Okay, so for our last section of Chapter 9, what we're going to be talking about is, first of all, what we call the imaginary unit. Now, the imaginary unit we use when we are dealing with the square root of a negative 1, okay? And the square root of negative 1, that can be simplified to the imaginary unit I, okay? This is considered your simplified radical for the square root of negative 1. Now, if we were to take I and raise it to a higher power, let's say take I and square it, that would equal a negative 1. And this would be considered your simplified expression. So whenever we see the square root of negative 1, we will simplify it with an I, the imaginary unit. And whenever we see I raised to the higher power of 2, I squared, that can be simplified to just a negative 1. You may recall when we were working with radicals earlier, when we took the square root of 4, we said the answer was 2. When we took the square root of, let's say, 36, we said the answer was 6. And when we first talked about radicals, and let's say we took the square root of a negative 4. Back in section 9.1, recall what our solution said. We said that there was no real number. Okay? And that's still true. In the real number system, we cannot take the square root of a negative 4. But now when we move over into this imaginary number system, the imaginary unit, by taking the square root of a negative 4, that's the same thing as, let's say, taking the square root of 4 times the square root of a negative 1. Because we know 4 times the negative 1 would give us the negative 4. And just like before now, the square root of 4 would be 2. And now that we have this imaginary unit, the square root of a negative 1, we can simplify that to 2i. So now the square root of negative 4, we can write as the square root of 4 times the square root of negative 1, and that's going to equal 2i. That would be your simplified radical. If we had the square root of negative 36, once again, that would be no real number, but now that we know we have this imaginary unit, we can go further. And we could say that the square root of a negative 36 is going to equal the square root of 36 times the square root of negative 1. And since the square root of 36 is 6, we could simplify that, as well as now the square root of the negative 1, that can also be simplified to just I. And so our answer would be 6i. We can also do this with, of course, the non-perfect squares. Remember when we took, let's say, the square root of a positive 48, we would break that up into the factors, let's say, square root of 16 and the square root of 3, and that's how we got 4 square root of 3 as our simplified answer. Well, if we were to take the square root of, let's say, a negative 48, once again, initially, we would have had to have said no real number. But now that we can go further because of this imaginary unit, that the square root of negative 1 equals the simplified version of I, we can take the square root of negative 48, and we can write this as the square root of 16 times the square root of 3 times the square root of a negative 1. Because if we were to multiply the 16 times the 3 times the negative 1, that would give us back the original radicand of the negative 48. And now we want to simplify what we can. Well, the square root of 16, that could be simplified to 4. The square root of the negative 1, that could be simplified to the I. We cannot simplify the square root of 3, so that just comes along the square root of 3. So now our answer would read 4i square root of 3. So that's the importance of this imaginary unit. It introduces us to this imaginary number system, and it's going to also lead us into what we call the complex number system. So you have seen many different number systems. Starting back as early as when you first started math classes, remember, you learned about the counting numbers and then the whole numbers. Then you learned about fractions and decimals. And then you learned about integers. Those, of course, are the positive and negative numbers. Then, most recently in Chapter 9, we've been working with this irrational number system, the radicals. Well, for our last number system that we're going to talk about, we are going to talk about what we call the complex number system. And complex numbers have a particular form. It looks something like this: A plus BI. Now, the A is considered the real part. The BI is considered the imaginary part. So those are the two parts that make up your complex numbers. For example, we could have maybe 5 plus 2i. That would be an example of a complex number. I could have negative 3 plus 7i. That would be an example of a complex number. I could have maybe 5 minus 8i. That would be an example of a complex number. Or I could have, let's say, negative 2 minus 9i. So here are all different examples of complex numbers. And if we were to identify the part that is real and the part that is, of course, the imaginary part, we could do that. The real parts would be the 5, the negative 3, the 5, and the negative 2. Those are the real parts of these complex numbers. The imaginary parts would be 2i, the 7i, the negative 8i, as well as the negative 9i. Those make up the imaginary parts of your complex numbers. So, like I said before, your complex number involves both a real part as well as an imaginary part. Now let's take a look at performing some basic operations, the 4 basic operations of adding, subtracting, multiplying, and dividing of complex numbers. For example, let's say we take 2 plus 3i plus 5 plus 7i. We want to add these two complex numbers together. Well, all we have to do is something very, very simple. We have to combine like terms. We want to combine the real parts, and we want to combine the imaginary parts. And we've done something similar to this already when we were adding and even subtracting polynomials. We basically had to combine like terms. So if we were to add these together, we would take the 2 plus the 5, and that would give us a 7. Then we would have to take the positive 3i plus the positive 7i, and that would give us a plus 10i. And that would be the sum of those two complex numbers. Let's do another example. Let's say we take the negative 3 plus 7i, and we want to add to it, let's say, 6 minus 8i. We want to add these two complex numbers together. Once again, we're going to add the real parts. Excuse me. Excuse me. The negative 3 plus the 6, that would give us 3. Then we would want to take the 7i and add to it the negative 8i. Well, 7i plus the negative 8i, that would give us a negative 1i. And that would be your sum of those two complex numbers. Now, if you think adding is easy, subtraction is just as easy. For example, let's take the negative 3 plus 5i complex number, and let's subtract the 8 minus 6i. Once again, we're going to combine like terms, but we're going to combine them with subtraction. So we have to take the negative 3 and we have to subtract the 8. Well, negative 3 minus 8 would give you a negative 11. Then let's take the imaginary parts. Let's take the 5i and let's subtract the negative 6i. And if we do that, 5 minus a negative 6, that would give us a plus 11i. And that would be your answer to the difference of these two complex numbers. Let's just do one more. Let's say we had 8 minus, let's say, 3i, and we want to subtract maybe 10 minus 4i. Once again, we want to combine these like terms, these like parts. So if I take the 8 and subtract the 10, that would give us a minus 2. And then let's take the negative 3 and subtract the negative 4. So the negative 3i minus the negative 4i, that would give us a plus 1i. And that would be the answer to these adding and subtracting of complex numbers. So like I said, when we add and subtract, basically you want to combine like parts. You want to combine the real parts and you want to combine the imaginary parts. And like I said, this is very, very similar to what we did with adding and subtracting polynomials. Well, let me pose you this question. What if we wanted to multiply these complex numbers? This might look familiar as well. Let's say we want to take the complex number of 2 plus 5i and we want to multiply it with a 3 plus 7i. Now, we saw problems like this in an earlier chapter, where once again we were multiplying a polynomial, a binomial, with another binomial. And think about what we had to do there to multiply the polynomials. That's right, we had to FOIL. So we're going to have to FOIL these complex numbers. And there's one very important thing that we need to keep in mind. Whenever we have an I squared, I had said earlier that I squared can always be simplified to a negative 1. This is going to be very important. Okay? So whenever we multiply an I times an I, we're going to get an I squared. And I squared can be simplified to a negative 1. And let's see what effect that will have on our answers. So let's start by multiplying the 2 with the 3, and that would give us 6. Then we have to multiply the 2 with the 7i. That would give us a plus 14i. Next, let's multiply the 5i times the 3. That would give us a plus 15i. And now if we multiply 5i times the 7i, that would give us a plus 35i squared. Because just like when you multiply x times x, you got x squared. When we multiply I times I, we would get I squared. But we're not done with the problem, because we want to always simplify as much as we can. Well, we see here in the middle, we have these like terms. Okay, so we're going to be able to work with those. But also, we see this I squared. Okay, and I squared, which is being multiplied with the 35, since the I squared equals a -1, this would be the same thing as if we were adding the 35 times a -1. And so now, if we were to combine the 14i plus the 15i, that would in fact give us a positive 29i. But now let's take a look at this 35 times the -1. That would give you a -35. And when you combine the -35 with the +6, that would also give you a -29. So by multiplying these two complex numbers together, we get -29 plus the 29i. Let's do another one. Let's say we have 6 minus 2i being multiplied with 3 minus, let's say, 4i. Once again, we will FOIL this together. 6 times 3 is 18. 6 times the -4 would give you a -24i. Now we have to multiply the -2i with the 3. That's a -6i. And now we have to multiply the -2i with the -4i, and that would give us a positive 8i squared. Well, once again, we have to simplify. We're going to keep in mind that wherever we see an I squared, that's the same thing as a -1. They are equivalent. So now we're going to have the 18, the minus 24i minus the 6i. Those are your like terms. So that would be combined into a -30i. And if I squared is -1, and that is being multiplied with the +8, that would in fact give you a -8. And so, when we combine these final like terms, 18 minus 8 would give us a 10 minus 30i as our solution to the product of those two complex numbers. Let me give you one to try on your own. Let's say we want to take 4 plus 2i, and we want to multiply that with a 3 minus 5i. Take a few minutes, pause the video at this point, and see if you can work through the problem. Once you are done working through the problem, check back and see how you made out. So, what you want to do is multiply, FOIL it out. 4 times the 3 would give us a 12. 4 times the -5i is a minus 20i. 2i times the 3 would give us a plus 6i. And 2i times the -5i would be a minus 10i squared. And now let's see what we can do. Once again, we have these like terms in the middle. So we have the 12. When we combine the like terms of the imaginary units together, -20 plus 6 would give us a -14i. And once again, the I squared, which is the same thing as a -1, is being multiplied with the -10, so that would actually make it a plus 10. And when we combine the like terms of 12 plus 10, would give us a 22 minus 14i as our answer. I want to take a look at one more multiplication problem that's special, okay? Let's say, for example, we had the following. Let's take 2 plus 3i, and we want to multiply that with, let's say, a 2 minus 3i. Now, this is going to be a special case, one that we will find useful. We are still going to have to FOIL these out, but there is something special about these two complex numbers. They look very similar, okay, in that the first numbers are both 2, the second numbers are both 3i, but you'll notice the sign that's in between them are opposites of one another, okay? And we saw something like this in the last section when we were dealing with the division of radicals, and then when there was a binomial in the denominator. And we had a special word for when the first numbers were the same, when the last numbers were the same, and when we had one positive and the opposite one negative. And that word is conjugates. Okay, so once again, what we have here is an example of what we would call complex conjugates. And let's see what this is going to do to the overall answer. And if I multiply 2 times 2, we get 4. If I multiply 2 times the negative 3i, that would give us a minus 6i. If we were to multiply 3i times the 2, that would give us a plus 6i. And now 3i times the negative 3i, that would give us a negative 9i squared. Well, the negative 6i and the positive 6i, since they are opposites, they're actually going to cancel out. And we know now that the negative 9 times the I squared is the same thing as negative 9 times the negative 1, which really is a plus 9. And when we take the 9 and add it to the 4, that's how we get our final answer of 13. So in the previous problems, when we were multiplying the complex numbers, I believe we started up here when we were FOILing. Here you'll see that when we multiplied these complex numbers, the answer took the form of a complex number because there was still an I. When we multiplied these complex numbers, once again, our answer took the form of a complex number, A and BI. When we multiplied these complex numbers, okay, once again, our answer took the form of a complex number, a real part, an imaginary part. However, when we multiplied these special complex numbers, these complex conjugates, we didn't have an imaginary part left over, okay? What did we have? Only a rational number. And this is going to come in handy for our very last topic of Chapter 9. And that, of course, after we add, subtract, and multiply, we have to talk about how we are going to divide complex numbers. For example, if I was to have the number 5, and if I was to divide it by a complex number of, let's say, 2 minus 4i, here we are dividing by a complex number. In essence, remember, since I is the same thing as a square root of a negative 1, this is basically telling us that we have a square root in the denominator, which is not possible. We don't want to express our answer with a radical in the denominator, or an I, for that matter, in our denominator. Once again, what we're going to have to do is to rationalize the denominator. Basically, what we're going to look to do is to eliminate any i's in the denominator. So we want to eliminate I in the denominator. That's how we're going to rationalize it. So, once again, what we're going to have to do is multiply by a very special form of the number 1. And the form of 1 that we will have to use will have to be in the form of the conjugate of this denominator. And recall, the conjugate looks very similar in that the first term has to be the same. The last term also has to be the same. The only thing that we change for the conjugate number is we change the sign that separates the two. And since here in the original problem we had 2 minus 4i, that means the conjugate will have to take the form of 2 plus 4i. That's the form of 1 we're going to have to use. So now let's see what this is going to give us. If we want, we can keep the 5 on the outside. When we multiply, we're going to have 5 times 2 plus 4i. We'll leave that alone for now. Now let's actually FOIL the conjugate complex numbers. If we multiply 2 times 2, that gives us 4. If we multiply the 2 with the positive 4i, that would give us a plus 8i. Now let's go and multiply the negative 4 with the positive 2. That would give you a negative 8i. And now lastly, we have to multiply the negative 4i with the positive 4i, and that would give us a minus 16i squared. Now let's see what we can do to simplify this a little bit further. Well, in the denominator, and I'm going to have to bring this down below. In our denominator, the 8i and the negative 8i will cancel. What can we do with that negative 16i squared? Well, remember, since I squared is the same thing as negative 1, that negative 1 is being multiplied with the negative 16, which would give you a positive 16. And the 16 and the 4 can be combined to form the number 20. So in our numerator, we have the 5 times 2 plus 4i. And what could we do to simplify? Well, if we want, we can simplify the 5 and the 20. 5 goes into 5 once, and 5 goes into 20 actually 4 times. So we would be left with a 2 plus 4i divided by 4. That would now satisfy the fact that we have rationalized the denominator. We don't have any radicals in the denominator. We don't have any i's in the denominator. And that's dividing complex numbers. Okay? So the complex number system isn't as complex as it sounds. It acts in very similar ways to polynomials, that when we add and subtract, we have to combine like terms. When we multiply, we have to use foiling, just like before with polynomials. The only major difference is, of course, the dividing by the complex numbers. That basically is looking to eliminate any i's in the denominator, so we have to rationalize the denominator by multiplying, remember, by what we called the conjugate. So that completes section 9.8 as well as all of chapter 9. Okay. Do take a look at the homework that goes along with this particular section and email me, please, any questions that you may have. Be well.